Okay, let's start. Last session we have started with assembly technologies. So in assembly, I'm going to treat mainly two different applications, to say it that way. One is to mount chips onto substrates, and in that case, it's mostly bare chips. We have already seen that it is necessary when we accomplish packages where we have a lead frame and a chip is attached, and we didn't go into the details of that technology too much. Here, that is two examples from previous PhD works in my lab that were radio frequency transistors. One is a silicon device, the other is a gallium nitride device. Both are devices which have a high power that is switched, and also high power that is dissipated as heat. And of course, in these cases, the heat conductivity of the substrate material must be high, but also the heat conductivity of the die attachment must be low. So here, that is die attachment technology, and that can be done by soldering, or by transient liquid phase bonding, or by silver sintering. We will see that in more detail. And the other technology, which covers the majority of all applications, it is surface mount technology. That means we have devices, and these devices are purchased in most cases via distributors. And on the other hand, a company producing such a circuit will develop the printed wiring board, and then purchase that printed wiring board, and on that base, both parts are put together in an surface mount technology assembly line. And in that way, we have you could say we have a very big toolkit of devices we can purchase and we can combine. And so any combination that is desirable, or any functionality that is we can think of, can be accomplished as long as we can have the corresponding semiconductors we need for that. Okay, presently we have a certain crisis, because semiconductors are hard to purchase. So there is an under coverage of the need we have in the market. And to that purpose, all of the economy is throttled down a little, just due to the lack of such devices. I was at a small conference yesterday, and they and some of the people reporting there were claiming that it is really hard to get some devices, and sometimes circuits have to be redesigned just in order to be able to give something to the customer. Okay, that's two technologies, and normally the whole technology works out fine. So we have already seen the basis of soldering, that is wetting with a solder, and solder has a low melting point. And that's where we ended last time. That was different solders. Let me say that solder here, in many applications, it was the standard solder in surface mount technology. before we changed over to lead-free solder alloys. In another alloy from that era, which was very important and which is still used frequently, for instance, in hand soldering, is eutectic tin lead alloy. So normally for commercial applications, it's forbidden, but it has quite a number of advantages. For instance, it solders well. It has a relatively low melting point, but on the other hand, not too low. And so it was quite a hardship to change over to another alloy when we introduced lead-free soldering. The main reason is for these two solders we had previously, we have a melting point of 180 degrees centigrade. And now we have a melting point of 220 degrees centigrade. And that is 40 degrees higher. And that poses high stress on the devices. So you must keep in mind the devices, for instance, the molded devices, they were designed to be soldered at 180 degrees centigrade, or better, maybe 200 degrees centigrade, because soldering temperature always must be somewhat higher than the melting point of that solder. Okay, but it was accomplished, and now we have either a eutectic tin silver or near eutectic tin silver copper alloy, which is, I would say, that's more or less state of the art, and that is typically called something like SAC 4 or 5. On the other hand, we have the need for solders which have a high melting point. The reason is that inside a package, we must have a higher melting point than on the pins on the outside. Sorry. Then on the pins on the outside. So the solder alloy for doing die attachment was typically a lead, a high lead content solder alloy, roughly having around 90% of lead and around 5 to 10% of tin, in order to lower the melting point and in order to increase strength, and also silver in order to improve these properties. All of the properties of these solders are very similar. So you could say CTE is somewhere around 25 ppm or 10 to the power of -6 per Kelvin. Thermal conductivity is somewhere between, let's say, 44 and 70. So in the end, really, nobody knows precisely, because every time someone measures it, you get a somewhat different property that mainly depends on how you did the heating, how you did the soldering. And also it's important to note that when you have a solder material in a real solder joint, it has different properties than when you make a piece of that solder material and measure that. That's a certain problem. On the other hand, let's say whether it's 50 or 70 doesn't make much of a difference, for instance, for the thermal conductivity. Electrical conductivity also, we have some scatter here. It's somewhere 10 to the power of 7 times, or 5 to 7 times 10 to the power of 6 per ohm meter. I would say for all applications, that's sufficient. So you don't have to care very much if it changes a little. And the tensile strength also here given around 30 Newton per square millimeter. Also sufficient for all cases. You can say it's of course much weaker than steel, for instance, also much weaker than silicon itself. But on the other hand, as the material is soft, you can avoid to build up stresses that are significantly higher than this strength of the solder material. Okay, but what is important most important is the melting point or melting range. So we have seen here already 3 different ranges, and we know why. And there is another alloy which is based on indium. Indium has a melting point of roughly 150 degrees. When you alloy something in, so you get some eutectic alloy, for instance, indium tin or indium silver, then the melting point can still be decreased. And in that way, we can have low melting point alloys. In the end, over the years, there was always demand for low melting point alloys in order to, when you have sensitive devices which don't tolerate high soldering temperatures. But that's only, let's say, a small fraction of the market. Indium solders are mainly used for so-called cryoelectronics. That is electronic systems that are working at very deep temperatures. So some kind of sensors for magnetic sensing, or also they are working in liquid nitrogen. But on the other hand, you also have electronics, for instance, quantum computers. They work near the absolute 0 point of temperature. And for that, you cannot have normal solder alloys because they become very brittle. And here indium alloys are better. They are more ductile even at low temperatures. Cryoelectronics, for instance, is also used in when you have infrared cameras, for instance. Yeah, so these are cooled down either with a Peltier cooler or with liquid nitrogen. And here we also often have indium flip chip bumps, for instance, in order to tolerate these stresses at low temperatures. Okay, but now let's come to the process of surface mount technology. And the main question is, how do we get devices on a printed wiring board? Yesterday I was visiting a company which does such services as which is also called contract manufacturing. So you can make a design, purchase the chips, and give all of that to that company, and they do the assembly and also the testing for you, and that is so-called EMS company, which means electronic manufacturing service. And there are quite a number of such companies around here, around Freiburg, because we have a very important electronics industry around here. Okay, how can we accomplish it? So what we need is, first of all, the device and the printed wiring board. And when we have that, we need some other helpful equipment and also some material. The equipment we still need is, of course, machinery for that, but also we have something that is specific, which is a printing stencil or a printing screen. And with that stencil or screen, some solder paste is printed on the locations to be soldered. So here in the image, it is screen printing, but normally, as we will see, it's mostly stencil printing. So we have a pattern of that paste. Typical value is somewhat below 100 micrometer of paste thickness. And that paste is wet and tacky. So as I said, most pastes we used in assembly and packaging are like toothpaste, yes? That you must be able to get a nice pattern of that, but the pattern after the printing must be stable and must not run away. So not to create defects. On that printed paste, we put the devices. Devices are set by a machinery, which is a so-called pick and place machine. Of course, it's an automated machine. There are two types of, let's say, positioning. One is you just program some coordinates and you know these coordinates are correct, and then it puts them there. But if you gave wrong coordinates, of course, you place it in the wrong place. On the other hand, modern machinery, they have a vision system, they have pattern recognition, and this equipment looks where the pads, where the paste are, and adjusts the location to pick and place. So that's especially important for the bigger devices. So in these cases, it's a controlled pick and place. After that, the board, which is placed on some kind of a belt, is run into the soldering oven, and here it is heated. So soldering is not a batch process, but it is a continuous process where the printed wiring boards run through a tunnel oven, and at least the top side of that board is molten. The solder, of course, only. And then when we only want to have a single-sided board, we would be finished. But in most cases, what we do is the complete board is flipped, and the second process, and the process on that side is done a second time, but with the other devices on the back side of that board. So typically, on the one side of the board, we have more the bigger components like the integrated circuits. And on the other side, we have more the smaller devices. Also, we must keep in mind we need other soldering parameters for the big and for the small ones, because the small ones heat up much faster, for instance. Okay, so we can go through that reflow process twice, and that's state of the art. But there's also another process which is so-called wave soldering. Here, after the first soldering, we deposit some dots of an adhesive, but that's only an auxiliary material. On the adhesive, we put the devices. So in most cases, it's just small devices like ceramic capacitors or small resistors or diodes or such thing. And then we heat it again in a tunnel oven. And so the devices are fixed. And then the whole thing is flipped again. And the board is run over a so-called solder wave in a wave soldering machine. Solder wave is liquid solder material is pumped up. So we have like a small hill of solder flowing up in that machinery, and over that small hill of liquid solder, the printed wiring board is moved and it's just touching it. And so you could say this is a solder wave is just licking along that surface of that board, and that is enough to have a wetting and to create solder joints, which are then during consolidating during the cooling down. Question: should we close the windows? Would it be better for? So we either suffocate or we get deaf, but here I would prefer silence. Thank you. Okay. So you could say wave soldering is not so important anymore because the devices become smaller and smaller, and then wave soldering creates more soldering defects than reflow soldering. On the other hand, all of the automated soldering processes that were introduced many decades ago were just wave soldering, and also the complete through-hole technology was done by wave soldering. Wave soldering is often used as a so-called local wave soldering. So we have only a very small solder wave. And for instance, if we have special devices which must be through-hole, for instance, we have a transformer or so where the pins must come through the board, then we use wave soldering. So it's still in use, but the most important process, of course, is reflow process. Here we see that's a cut through the edge of a chip scale package, and we can see the wetting angles here. They are relatively small, so it's narrow angles, and narrow angles always shows us that there was a good wetting in the process. There is a small pore here. We can see it here. Such a small pore, and if it's only a single one, it is absolutely tolerable, and it has no effect on the strength or on the conductivities of that solder joints. We could notice in any way. So you could say, so small pores are tolerated, but bigger pores, of course, not. Okay. Yeah, good point. There are quite a number of reasons. For instance, there could be a contamination in that location. That could be a solid particle, but it also could be an organic particle. And if organic particle or even contamination by something having to do with water will always lead to development of a little gas, and that gas gives a bubble. Yeah. Nothing. You talk about that adhesive material here. I know that's a auxiliary material that is just stable enough to survive all of the process steps, and further on, that material is just the only reason we have that material is that when we flip that board, the devices will not fall into the solder wave. In the end, nothing that is worth to notice here. Let me say it that way. One last thing which is important. For instance, the company I visited yesterday with that workshop, they are doing lots of assemblies for aircraft industry. And in aircraft industry, we have high safety requirements and reliability requirements. And in order to improve reliability, it is important that the boards are very clean. So typically in soldering, state of the art is we use no clean solder pastes. So for normal applications, we just leave the solder, the flux residues on the board. But for special applications, we need very clean boards because ions always promote corrosion. And for these applications, the boards are cleaned. In former times, we used what is it? Fluorohydrocarbon compounds, which lead to the ozone hole. Yeah, and these are forbidden for quite some time. And now, if it is cleaned, normally we use some kind of watery solution. In fact, the board is put into something, let's say, a little similar to a dishwasher. Yeah. So the dishwasher equipment manufacturers also, like Miele, for instance, they also create dishwashers for electronics industry, but here not dishes, but printed wiring boards are cleaned. And that's important. So in order to improve reliability, it's especially important if we do some protective coating on the board. Yeah, so it's not sensible just to cover the dirt you have on a board just with a layer of plastics. Yeah, that's not good. Yeah, before you put that on, you must thoroughly clean it, and that's a way why cleaning is still in some applications optional. When I entered that business of assembly and packaging, that was around 1990 or so in industry, my first project was to eliminate cleaning from the chain of production. And the main trick to do that was use better fluxes, which are needed for soldering. Okay, but here in that previous image I showed screen printing, but in the meantime nobody does screen printing anymore, but we use stencil printing. The reason is screen printing is more for so-called thick film technology, and thick film means 10 micrometers or so. But for surface mount technology, we typically need something up to 100 micrometer. So we need thicker layers, and these cannot be accomplished by screens. And so we have so-called stencils, which is just metal sheet, which has openings which are cut out with a certain process. And then we put that sheet of metal directly onto the printed wiring board. We put on the solder paste, and here is that so-called squeegee. That's like, yeah, it looks like a ruler made of rubber, and that is shifted over the board. We can shift it in only one direction, or we can shift it back and forth. And in that way, the paste is pressed through the openings, and then the stencil is taken away, and so the solder paste stays on the locations which are to be soldered. So typically, the copper pads or the tin coated pads should be covered completely with the solder paste. And yes, let's have a further look. No, the screen printing is, we have a screen, it's a mesh, and that mesh is coated with a photoresist, and that photoresist is developed by photolithography, and then we have openings, but we have the wires in between. But in some locations, the wires are covered with that resist, so we have it closed, and in other places we have openings. The screen is above the board, and it is pressed down, and when the squeegee goes away, the screen hops off, yes, in German, Absprung. And so the stencil is put on flat onto the substrate, and the stencil is made of metal, while the screen you have, it is metal wires covered with photoresist. Yeah? And some years ago, we had in Germany, we had a very big project where all of the companies, of the big companies involved in electronic manufacturing were participating. And one of the things we investigated was what is the effect creating defects in soldering or at the end of that surface mount technology process. And it was a little surprising, yeah, because in previous years, all of the concern was always on solderability and wettability. That means the surface you have, is it wettable, or do you have wetting defects? And wetting was mainly improved either by stronger fluxes, and second is you can also increase temperature a little, and then the activation of the flux is stronger, and it solders better. On the other hand, so the soldering itself and the the process itself also can lead to defects. For instance, if the temperature profile is not proper, that can be the soldering itself. But the components and the boards, where we previously thought they are the main concern, they were not a real problem anymore. 6% of all soldering defects we found afterwards were a result of non-solderability of components. The soldering process itself, it accounted for 15% of all defects. Pick and placement is also sometimes a problem, because also a pick and place automat can make a mistake. Or sometimes, for instance, we always have these belts where the devices are in, and sometimes, for instance, a device is flipped when it is in that belt. And so if we have a dump pick and place machine, it doesn't notice, and no matter what the orientation of the device is, it places it. Yes, so that's a placement failure, and in that way placement, or for instance, the machine tries to grasp the device but doesn't get it properly. Happens sometimes. For instance, there is a uncleanliness or so, it slips, and then the device is not placed properly in the right place, but a little to the side or so. And in that way, we can also have some placement errors. But it was found out that when you go for reflow process, the solder paste deposition, and that means stencil printing, is the main concern of that leads to defects we can see at the end of the process. Now let's have a look at the stencils. That is also from that project, from the initial, but it shows us still the how we can get a stencil. So one thing is we can take that metal sheet, put on a photoresist, expose and develop and etch it. And then we get the openings just etched into that 100 micrometer foil of stainless steel. What was considered better for some time, but that was quite expensive, that was electroplating such stencil. So that is you could say it's a semi-additive process, and you build up by electroplating mostly into a mask of some thick resist. You can build that up. Quality is also very good. On the other hand, you can laser cut these stencils. What you can see here is an early example. So the sides here of that laser cut are not so good, but in the meantime, situation has improved. I would say modern laser cut stencils are as good with respect to surface quality as previously the etched or electroplated ones. But what is a big advantage of laser cut stencils? Yeah, okay, why? Time? So, yeah, that's not really the reason, but to the left and to the right for these processes, you always need a photoresist. Yeah, you must expose the resist, develop it, then do the etching or plating, maybe some back etching process. And again, that always needs you some special, yeah, like the resist. On the other hand, laser cutting, what are you doing? You have your computer aided design of the printed wiring board that is modified a little, and then that design can just be used to directly drive a laser which is directly cutting away the material where you don't have it. You do not have a mask, you do not have a resist, nothing. You just cut it off because the laser is just programmed, and the programming is just done automatically from the layout of your board. Yes. So in fact, in the meantime, you make a design for your board, you upload it to the supplier of the printed wiring boards, and then you have a screen, and on that screen there is one question which you can tick: need solder mask or not? So printing mask. If you tick it yes, that system automatically creates the design of a mask. So that means it calculates in which locations you need to cut out something from the sheet. And then you pay €2 more and you get a mask you can use for printing. That's very convenient. Of course, then you still have to specify, do you need a mask for one single, or do you have a compound where you have 8 boards side by side, or yeah, what's the frame size of your printing machine and so, but in the end you get that, and it's quite convenient, and the basis is mainly that laser cutting, and in that way most of the stencils now, or I would say almost all, are laser cut. Here's an example in our project on that production technology. We were aiming at, yes, what's the trend in electronics, as we have seen in microelectronics, more IOs, yeah, higher frequency, more IOs. If you want to have more IOs, you must have smaller pitch, because you do not want to have a device that is 1 square meter big. Yes, you cannot put that processor on your printed wiring board, so you need a small device. And having it smaller, you need smaller structures also for the interconnection. And here the trend was, for instance, when you have the pins around the device, the trend was 0.3 millimeters pitch. That means you have 150 micrometers of width of that leg of that device and 150 micrometers of clearance. Yeah, that means 300 pitch. That means here that width, also you print, should be relatively precisely 150 micrometers. So you need such a pitch, you need a stencil which is laser cut and which is so fine. You can get it, but what you get in the end is many defects. Yeah, here you can clearly see, for instance, here already a bridge is formed. When you heat that in soldering, you will have a solid bridge. Yeah, that's one of the most important defects. And here you have a bridge, and also that will pose big problems. And if you made such a mistake on such a device, there is hardly any possibility for rework. Yeah, for instance, if you resolder it with hand or so, you bend the leads, and so there is hardly any possibility for rework for such a thing. And so the complete idea of making just finer pitch, if you want to have 500 IOs on a device or so, that was not possible. Clearly, there was another trend, which was array arrangement of the IOs. We can see that here, if we have, for instance, 400 IOs, then we do not have, let's say, 400 times 0.3 millimeters periphery, but we have to arrange 20 by 20 devices, and so the length of one side is just 20 times somewhat. And now if we say, okay, the pitch is 1 millimeter, then the device is only 2 centimeters or 2 centimeters and a little large. And that means device stays smaller, and then we do not deal with 300 micrometer pitch, but here we deal with 1 millimeter pitch. And here, if we have such a small, let's say, inaccuracy of the printing, nobody has to care about. Yeah, that's while the same inaccuracy here is deadly for the board. Yeah, and in that way, the trend went towards array technologies. You could just say, okay, that's the way it is, how we did it. In fact, it was not so easy because one thing was ball grid array technology was not as reliable as quad flat pack technology. Just with respect to temperature cycling, cycling through 3000 times to 125 degrees centigrade. So in the first ball grid array solderings, it was not possible to get the reliability of the other devices. And we had to work on that. And the second thing is also important. If you have 400 IOs on a periphery, yes, you could say you must get the signals somewhere. And now bringing away 400 IOs to all directions, you can even do that on one layer on your board. Yeah. On the other hand, you have an area of 2 by 2 centimeter with 400 IOs. You cannot get the lines side by side, but you need a board which is a multi-layer and which has very many fine wires under the ball grid array in order to get all of the pins connected. Yeah. So that means you need other printed wiring boards, at least of higher wiring density. And so that's a very good example. You can have a good idea. That idea seems to be quite simple, yes, but in fact, to accomplish it there are many restrictions against it, and that always means it can be solved, but it's lots of work. Typically, it was several years of development work. Yeah. So let me say the ball grid array was invented at the beginning of the 90s, and it really was introduced in automotive technology. You could say maybe it was established 2010 or so. Yeah, there's 20 years between it. In other technologies, it was earlier, of course, but you normally don't have a Intel processor which is made for a PC, for instance, or AMD processor. You will not find it in a car. Okay, the soldering. What we can see here is a standard soldering profile. We have already seen in the ceramic materials that you cannot just go to the temperature and say, okay, now it's sintering or soldering. You always need a certain profile that is adapted mainly to the chemistry of that material. And so you heat initially with a certain rate, maybe up to 120 to 150 degrees centigrade. In that range, the paste is dried. If you do it too fast, there is such a high pressure of the evaporating solvents that the devices are just flying away. Yeah. So you need a certain rate. That flying away or flipping up of the devices is so-called tombstone effect. So the rate is limited. Then you typically have a certain preheating rate. So you do not go just to the soldering temperature, but you stay a little below. But at that temperature, the board is soaked with heat. Yeah, because in the end, we want to have a relatively fast soldering process. Then after the board is soaked, and the time of soak, of course, is longer when the devices are bigger, then we heat up fast. And maybe shortly under or a little under below we reach the soldering temperature, the flux is activated. And then the flux becomes active, and a little later the solder material becomes liquid. And then, for instance, here in that solid line curve, we go to 230 or so, and that's a typical profile we have for a leadless solder alloy. And the time we are at soldering temperature is relatively short, typically maybe 20 seconds or so. And after that, we cool down, but not too fast in order to avoid thermal shock to the devices. So in the end, again, such profile shows us we have to regard physics and chemistry of that system in order to get a proper soldering. But if we do that, we can expect that the number of defects we create is very low. Let me have a look. Yes, that's such an oven here. That here is a tunnel in which we solder. Here's a control computer. That upper cover is just as a additional protection because that internal tunnel is hot. And here we see different profiles. So the profile is mainly depending on the devices we solder, you could say, and also a certain effect we have. A certain effect we have by the material that we solder. All of these controlled slope, some holding or soaking phase, and then the soldering phase itself. That's typically reflow soldering with convection. Convection means hot air, or in most cases, hot nitrogen is blown onto the board. Another possibility to do so as we see it here in principle, that's nitrogen that is heated, flying below some heating elements, and so it's convective heat transfer. What we also can have is using lamps. So for instance, some halogen lamps, they are quite strong. So when you are near such a lamp, your skin becomes quite hot. And if you have many of these lamps, you can even melt solder. And so we can have radiant heat. There's again possibility using short wavelengths. That's these halogen lamps where you can really see the light, or it's heaters like on your kitchen stove where you can hardly see the radiation, maybe a dark red or so. That's a long wave length. Heating both is possible, but presently the trend is more towards convective heating. Typically, such an oven is quite long. For instance, it has 5 to 7 different zones, which all have a different temperature, and maybe one zone is maybe half a meter to a meter long, and that means such ovens are quite long. There is one more possibility to do soldering, which is also which is a very good method, but which is you could say very specialized. That is vapor phase soldering. So people having glasses, being in the cold and coming into a damp room, they have condensation on their glasses. And yes, what you don't notice is that during condensation, the material on which the condensation is heated up. Yeah, for instance, you have a boiling pot and put a lid on that pot. The water will condensate at the lid, and the lid immediately also will have 100 degrees centigrade. But as it is a fixed point in condensation, we can say the temperature will never go beyond 100 degrees centigrade when we have condensation of boiling water. Okay, that's something very good. First of all, we can transfer lots of heat with that phenomenon. And on the other hand, we are absolutely sure we have no overheating. Yeah, the temperature will not go beyond a certain point. And now what people do in vapor phase soldering, they do not use water because here the temperature would be too low, but they use some organic substances, some kind of, yeah, what is it? Certain kind of alcohols, also higher alcohols, which have a high boiling point and high condensation point, maybe also around 230 degrees centigrade. And in that way, we can also do soldering. But the disadvantage one is we have to avoid that these substances come into the environment, and these substances are also expensive. So most of the companies don't go for vacuum phase soldering, even though it's better than reflow soldering, but it's more complicated and more expensive. Okay, I already mentioned the question of wetting. Wetting is important, and it was the key. Let's say improvement of wetting was the key to reduce the rate of soldering defects as a result of wetting defects. And that was one thing. And the second was control of wetting was key in order to eliminate cleaning processes. That means when you have better wettability of the devices, you can use fluxes which are not so strong. And all of that means that many processes must be controlled much better. But you always want to know something about wettability, and especially at times when we used wave soldering, there was some kind of dipping test where you could see how wetting works. For instance, you take a liquid solder bath, put on some flux and dip in a piece of copper, and you look at it and say, okay, it's wetted well, or it de-wetted, or so it's a qualitative judgment. Also, when you solder by hand, you can see, is it wetting well or not? But in industry, you want to have something quantitative, and to that purpose, a so-called wetting balance was developed. A wetting balance is a machinery which dips a piece of material into a molten solder. That can be also a small droplet or so, but it dips it in. And the forces for dipping are measured. And when you have such a, so on top here, you have such a load cell to measure forces. Yeah. So at a controlled rate, you dip it in. And when you dip in, even in the first let's say, fraction of a second, you never have wetting. That always takes a little time. And so you have two forces. One is the surface tension, and the second is the buoyancy, which push back. So, and pushing back here means a negative force. So dipping in, you have the pushback by the surface tension. You know that little bugs that can run on water by surface tension. So it's similar here. You dip, but it doesn't wet and go in. And then suddenly the wetting starts, and then the force goes to zero. That's like equilibrium. And then the force goes up, and that means the surface tension now, as it wets, pulls down. And of course, when the wetting is good, you have a higher force where the surface tension pulls, or the wetting force better pulls. And then it goes into an equilibrium. And then we have several properties we can take from such curve. For instance, we take the maximum force here either in equilibrium or after a certain time. That is relevant. And then we have the time until we have 2/3 of that maximum force. And that's a time constant of wetting. Why is it 2/3? Sorry? Yes. So we already had several times that exponential curve, which goes towards a limiting value, for instance, hardening of a resist or hardening of a epoxy or taking up moisture. And when we take the time constant using that exponential curve, it's always 63 and a little percent, and that's roughly 2/3. Yes. So maybe for some people who didn't study or so, but which have to evaluate such curves, 2/3 is easier than to take something from an exponential curve. And so you could say that's quite good estimation of the time constant of that process. Yeah. And in that way, the time constant of wetting should be in a certain range. That means if that time constant is too short, that typically means the flux is consumed before the soldering even starts. That's not so good. The second is when it's too long, that means the flux doesn't start to act when the soldering process is already finished. And that's also nothing we want to have. So the time of activation of such a material of the flux should be in a certain time window or time frame. And to that purpose, it's also important to take the time. But anyway, wetting should be relatively fast, within a few seconds. And so that's a good instrument in order to investigate two things. One is we have a standardized surface where we know it's good or we know it's bad, and we try out different fluxes and say that flux is stronger than that. Or on the other hand, we want to know how good a device is solderable. Then we take a standardized flux and compare different components, whether they solder well or not. And soldering well means high wetting forces and proper wetting time. So again, that is something which gives us information how good such a process is. In former times, bigger companies doing assembly had such wetting balances. Nowadays, they don't have it anymore. So when I entered that business, it was always you purchase something, you test and check whether it's fine. Is it wettable, and is the thickness of the tin sufficient, and that and that. So all of these quality departments had lots of equipment. You do not have that anymore. After a few years, all of that was abolished. And how was it brought under control then? Very simple, just by the contracts with your supplier. If the supplier supplies something of low quality, he has to pay. He has to pay for the analysis. He has to pay compensation for your losses. It's not just like you as a consumer that you, if it's not okay, you can get a second one or so, but there are additional costs, and typically in industrial contracts, someone supplying something not so good has also other costs to carry. And so all of the thorough investigation was put to the suppliers. Also, that's more efficient because the suppliers are specialized to the investigation of specifically their product. They have better comparison. How good was it yesterday? How good was it last week? While when you take an incoming inspection, it's always different, yes, and you never can be as precise. And if you have slight changes in quality, you will not notice it. You will notice, is it good or bad or so? But a supplier, it's better when he does it, yeah, and also he can immediately bring his production under control. And so in that way, all of that was previously incoming inspection is now for the buyer is now outgoing inspection or on production inspection for the supplier. That's how things changed in maybe in the 1990s, but that's still how it works nowadays. And it led to a significantly improved quality. We must also say that. Okay, what can we do wrong in solder joints? Here I have two examples. One is the surface mount devices. Like here, it's a chip. I would say that's a chip resistor. And you can have voids. That is a correct joint. So nice wetting angle, smooth surface. That line here, that's a so-called meniscus. It looks fine. So bend a little inward. And yes, also the meniscus on the underside. Here, the clearance between pad and location on the chip here is sufficient. That's fine. That's a so-called fat solder joint. Here we have too much solder material. Fat solder joint was mainly a result of wave soldering. Or of wrong design of the pad here. So if we print too much paste for the size of a pad, then we also have too much solder on that location. And then we can have a lean solder joint. That was also often in wave soldering. One had too much solder, the other had not enough. It also can happen in reflow soldering, for instance, if we have a line here and there's no solder resist, then the solder will be will run away by wicking, and that of course, when the solder is on the conductor line, it will no longer be in the place where it should solder, and then that meniscus here is missing, and in that way we can have lean joints. Unfortunately, when you have such a situation, normally in temperature cycles, both joints work against each other. And if they are equal, the load is distributed equally. But now you have a fat and a lean joint, they work against each other. And of course, the lean joint will fail much earlier than the fat joint. Yeah? So though the fat joint normally isn't a problem for the fat joint, but it's rather a problem for the second joint. And also in former times, that's also a good sign how clean your solder is. So in reflow soldering, you typically buy your paste and you know the cleanliness, yeah, because it's specified. When you do wave soldering, over time, impurities accumulate in that solder bath. Yeah, that solder bath can be 500 kilograms of solder, but as time goes on, you always have leaching of some metals because you always dip something into that bath. Yeah, and so you accumulate iron and aluminum and magnesium and sodium and copper and what else? Yeah, and nickel. And this gives a higher content. And at some point of time, you can see these impurities because then the solder joint is no longer shiny, but it looks a little, yeah, dull, you could say. And from that, for instance, some people are even they look at the solder joint and they can tell you what the content of which impurity is. Yeah, they can tell you it is 100 ppm of iron or so just from how it looks. Yeah, very interesting, but it's not so important anymore because we go for reflow soldering mainly now. Another thing is through-hole technology also requires good joints. That is, for instance, from a handbook of the European Space Agency. The value of a satellite is 100 million euro or more, and you do not want to spoil that just by a bad solder joint. And so, of course, all solder joints in a satellite are inspected thoroughly, and still we need through-hole technology for interconnectors, for transformers, and what else. And so it is specified. So when we have the solder, we must have a good, it is called feathering angle. So it's a wetting angle here. It must be significantly below 90 degrees so that then you can even compute wetting forces, and they are higher then. You must not have any unwetted areas. So everything that is wettable in principle should be wetted. And that fillet should be filled out completely. Also, you want to have good wetting on the pin and on the via metallization. On the other hand, that is something not so good. The circuit pad is partly unwetted. The lead is partly unwetted. The angle you have here, what can you see? It's going towards 90 degrees, or sometimes it's higher than 90 degrees. That's a good sign of bad wetting. What's the cause here? That it didn't wet. You can have, of course, always two principal causes. One is wettability of the devices is not good, or second is process is not good, and process not good means typically flux is not good. What would you say here for that right side? Is it the flux or is it the device? I would say, yeah. Why? I would say yes. Both parts are not wetted. Yeah. So it's some cause which is relevant for both. Yeah. So in fact, we have two parts to be wetted, and I would say it's not so probable that the pin and the pad are not wettable. Yeah. So in that case, I would say that gives you a first hint of what could be the cause. On the other hand, you could also say if both are, and if it's not the flux, then probably you have made a mistake in storage of your devices. Yeah, for instance, they were not stored in nitrogen, but they were stored in a damp atmosphere without special precause. Then you could say maybe both are not wettable. But again, just from some experience looking at these parts, after you have a problem, you can already see or have a hint what the cause could be. Yeah, that's also important because no matter what microanalysis you start, it costs you 500 to 1,000 euro or so to have that investigated with some equipment. Yeah, and that means just using common sense and some something you can see that's that helps. Again, here for the die attachment, for instance, here the chip is not wetted, or the substrate is not wetted. Here it's clear it's a chip or it's a substrate. Sometimes you have a gas bubble. Here again, you can have different causes. As I said, it can be an impurity. If you have a printed wiring board, if you have stored that in a too high humidity atmosphere, the water will gas out during the soldering. You could say it's similar to the popcorning effect, but it doesn't go into the polymer, but it goes into the solder material. So none of these is wetted. Then you have maybe such a problem. You can also have cracks between chips and solder. There are many possibilities. One of the possibility is after cooling, you build up too high stress between chip and substrate, and that just cracks something in here. And that can be a crack in the chip. It can be a crack in the interface. In some cases, also the interface is not strong. Yeah, then metallization of the chip doesn't stick well, for instance. Then you can have a crack not in the solder, but you have the crack here in between. But again, from just how it looks and where it appears, you can have already some information what the reason is. Here is another thing from soldering that is also some device, some kind of QFN device, quad flat no lead. That device, as it is a chip scale package, has also a quite big chip. We can see the chip here. Maybe it's not really a chip scale package, but almost. And here is a chip. When we look precisely, we see also the bonding wires here. You can see it. Here's a chip. And in the middle of that device, we have a copper plane. So it's not only the IOs are soldered, but also the ground plane is soldered on the board. Why do we have that? Yes, it's a heat dissipation, but what is important that there is no porosity, because a pore will not transfer heat properly. And especially we do not want to have a pore under a larger pore under the chip. To the left, that is, I called it low porosity. I would say it doesn't look so well. It can be done better. On the other hand, normally we do not accept more than 20% of porosity or pore area in that layer. But here to the right, we can clearly see there is too much of porosity, and that will clearly pose a thermal problem for the device. So when the device is, for instance, tested just electrically, that might be fine, but when it's in operation, for instance, at higher temperature and having higher power dissipation, it can be overheated. And as a consequence of overheating, it will fail soon. So you could say then it's maybe fatigue failure of the solder joint, but that's not the basic cause. The basic cause is the solder joint was bad. It had too many pores. Something interesting, what is also done in the meantime, when you have such devices, you can identify them. So if you say, okay, such porosity to the right is never sufficient, but you have a low porosity, you can take that as a fingerprint. So in the meantime, you could identify devices just by taking an X-ray. And for instance, let's say you take the 10 largest pores, and for the pores, you just measure the position and the area. And then that means you get 30 data values, or that's like a numerical word with 30 digits, yeah, or more. And that's sufficient to identify every chip, yeah. And the advantage is if you have a series number on chip, yeah, you can print that on or so. That can be faked, yes, but nobody can fake that. That's a so-called intrinsic mark you can have. So it's not frequently done, but we also have done some research on how you can use intrinsic marks for identification. And an interesting thing is when you use X-ray, you can even find that when the part is built into some equipment. Yeah, you solder or you X-ray the equipment, and you can get that information. So that's maybe not too frequently done, but that shows us what can be done and what sometimes is done. For instance, when we talk about not only safety but also security, for instance. Okay, that was on soldering. So let's say 90% of all assembly processes can be accomplished with soldering, but for some applications we need something better. And we have introduced silver sintering. So the main thing is, now let's come back to die attachment. We have a large chip, and that must be attached to to a substrate. And in power electronics, the most important criterion is the thermal resistance. The thermal resistance is a value that gives us information how much temperature is increased for every watt of power that is dissipated in the device. So the dissipated power is not the electrical power we have in that device, but it's a power that is lost due to efficiency losses. Yeah, so that means ohmic losses or so in the device will lead to self-heating, and now the thermal resistance gives us the temperature increase per every watt of lost power in that chip. And the power electronics people, they had several development. One of the development I have shown you, it's a direct bonded copper. That means, or direct copper bonded ceramic substrates, which have a high thermal conductivity. The copper distributes the heat very well. We can solder against it. Electrical conductivity is very good. All is fine. But there was one disadvantage when we want to have it live for very many cycles. So many is for me 10 million cycles of heating and cooling, or 100 million cycles of heating and cooling, like in railroad applications. Then a solder material is not sufficient. So solder material has fatigue. There will be cracks coming from here, and then when there's a crack, what will happen? The chip is detached. When it is detached, the thermal resistance will increase. When the thermal resistance increases, temperature increases. When temperature is increased, crack propagation is faster, and then very soon, when that has started, it's the end of the chip. So it will, normally it doesn't fall off, but it will just blow up or overheat and fail in that way. So one of the trends to lower thermal resistance in power electronics was making chips thinner. So you can say in the last 20 years or so, the thickness of such big chips was reduced from 0.5 millimeter, which was the standard chip thickness, to 50 micrometers, roughly. It's sometimes different. Some have 40, some have 60, some 70. So it's but I would say now 50 is a good rule of thumb. And that just reduces the thermal resistance in the silicon. But the effect, on the other hand, is not so high, because silicon is already a very good conductor of heat. Yeah. The second thing is, silicon has a thermal conductivity of 120 to 150 or so. The solder we have seen has 50. Yeah. So working on the solder would have much more effect than working on the silicon. But unfortunately, we cannot make the solder much thinner, because the thinner the solder is, the faster fatigue will be. Yeah. Because in that case, shear strain in the solder is higher, because shear strain is always displacement divided by thickness. Yeah. So make it thinner just increases shear strain naturally. So here we were in a trap, you could say. And that trap was eliminated by using a different die attach material. And I think the basic ideas of that die attach were back to Siemens company and University of Brunswick in Germany. And there was a famous PhD work on that, and they invented silver sintering. The trick was that when you have silver powder, you have to sinter, you can sinter it. We have seen what sintering is, for instance, in thick film paste, yeah, silver palladium or so. What's the temperature of sintering? Thick film technology. Yeah, very good, 850. But you would not like to do that on a IGBT chip or any other silicon chip. It would never survive it. So you must go down. But how can you decrease the sintering temperature? And there are two tricks. One of the trick is making finer silver powder going to 1 micrometer or lower. Then the sintering goes much faster, even at low temperatures. A low temperature for us here, let's start with 300. Yeah? The second is, if you still want to decrease it, you must address chemistry. And chemistry means you have some activators which improve the rate of diffusion of the silver in that sintering process. And that was done by, you could say, by industry. And so in the meantime, they have sintering pastes, which are very fine powder, micro powder, or even nano powder, and certain chemistry. And in that way, they are able to accomplish that sintering process in a temperature range, let's say between 200 and 250 nowadays. So just a rule of thumb. On the other hand, what you also need in that case, besides thermal energy, you must put in mechanical energy. And that mechanical energy is just pressure you put on. Here is an example. When we have that chip is pressed on with a pressure of 30 megapascal. So 30 megapascal, how many bar is that? Or how many atmospheres is that? 30 megapascal seems to be not so high, but it's 300 bar or 300 atmospheres. Yeah, that's high pressure. If we put that pressure on top of the chip, it will sinter well. You can also see on the sides where the pressure is not, it doesn't sinter so much. If you have only 10 megapascal for the same conditions, you have already some conversion of the paste to a more solid material. But here the material contains still 50% of porosity. So that means the strength of the material is not so good. But here, having such a material, you can create a layer which is almost a solid layer of silver. And silver is strong, and silver has the best thermal conductivity. Pure silver has 400. So that would mean silver is 8 times better in thermal conductivity compared to solder material. And that was a big progress. And so that's the reason why many high power modules are now using sinter technology. In fact, we do not know so much about the chemistry behind that sintering. The reason is chemical industry never gives out their secrets. Yeah, what we can see, of course, is the size of the powder or so that we can analyze. The rest is always a certain secret. Also, they have patents on it, and in that way, yeah, that unknowledge has certain disadvantages, of course, in some cases for the user, but in the end, it works, and that's what counts. Yeah. Okay, so sintering, we will see a little more next time, but I would say sintering is for power electronics. That's now the dominating process if you want to have really high power and high reliability. So that means it will tolerate very many cycles and many more than solder joints will tolerate. You have a question? Yeah. Yep. Yes. Oh, unfortunately, yeah. Here we see we have a lower hot plate and the upper hot plate. Here in between, you see the substrate with the chips on it, and it's just pressed together. Ah, yes. I would say normally the best of putting up such pressure is a hydrostatic pressure. Yeah. So if you would have a liquid, it would be best because you do not have points where you have high stress concentrations. But what we put in here is a certain, either you use some special silicone rubber, so it's a soft material, and if it's has a certain thickness, that material poses something similar to a hydrostatic pressure on top of the chip. And if the stress is evenly distributed, or the pressure, it will not damage the chip, because silicon if you put on a very even but very high pressure, it will not fail. Yeah, the failure always comes if you have a pointwise stress, or if you bend it, or if you pull it. But if you have compressive stress, silicon will be extremely strong. And also what is on and in the silicon is not damaged normally by such compressive pressure. And that means you need some layer in between. For instance, we either use a carbon sheet, or we can also use some rubber-like sheet, which is, of course, it must be heat resistant. Yeah, and it must transfer the heat from this machinery. But in the end, that works out well. So that's not really a problem. But it can become a problem. Okay. More questions? Okay, then thanks for your attention, and see you on Monday.